Okay, so what I want to do today is continue talking about applications as well as talking about where do you go from Calc 2. This is probably one of the easiest, classes in terms of trying to figure out what you do next. Calc 3 is the most logical alternative, but linear algebra is also defensible. There's a lot of wonderful things you can do. And so I wanted to use today to talk a little bit about what would you see in a Calculus 3 class? What are the new kinds of methods and problems? But more than that is talk to you about how do you think like a mathematician? How do you try to find a problem to study? A lot of it is you look at the world, you look at what's known, and you try to push it forward. You try to say, well, what can I do that's related to this? What would be a good next problem? And it is amazing how many times in my career I've just been able to be successful by looking at things that people have already done and ask, well, what's next? And you should always be thinking about this when you are reading materials, when you're learning a subject. The best way to learn something is to do. And even if it's a small extension, just writing up all the details and trying to do it, you're more likely to deeply understand what's going on than if you're just passively reading. So you're trying to be active and just always asking questions. If only 1 out of every 20 times it leads to a good question, that's still a tremendous success rate. All right. So we often say a proof rather than the proof. What is the best school for college football? No, the Ohio State University, where I was a postdoc for a year. So there we talk about the Ohio State. But in mathematics, we normally don't say the, we normally say a proof. There's usually many ways of proving things. So some of today's talk we've actually seen already in the semester, and I'll just go through those parts quickly. Different proofs highlight different aspects of the problem. And sometimes when you're trying to generalize, it's not clear which is the best way to view things. A paper I wrote a few years ago with some students, we tried to generalize the best results and it didn't work. And then we realized that for higher dimensions, we actually had to go back to an earlier argument that was weaker, but that actually generalized better. So as much as possible, try to explore, try to be active, don't be passive, play with things. Look at extreme cases. Special cases is often a wonderful way to try to get a sense of what's going on. And so we're going to start with the Pythagorean Theorem. I know you've seen this before because we've covered it in this class. All right, so if you have a right triangle, a squared plus b squared equals c squared, the only freedoms you have is which side you call a and b and which way you orient the triangle. And it's classical assumptions from geometry that if I rotate the triangle or translate the triangle, it's not going to change its area. And we start off with the concept that we know what an area is. An area of a rectangle is length times width. A right triangle is half of that. So if we rotate the triangle, two right triangles will fit together and form a rectangle. So the area of a right triangle is 1/2 base times height. And then you can generalize and show that this holds for any triangle. So why are proofs important? Well, they help us see the big picture. And also they give us some comfort that we can keep using this result. So we did the baseball lecture where we talked about the Pythagorean one-loss formula. Well, just because it's worked for many years doesn't mean it's going to continue to work. And so if you can come up with a proof, then okay, I know I can always use this. Or maybe you can prove special cases. As long as these additional conditions hold, I have the result. Right. So I think we've seen these slides before. This is the old proof from Euclid. This is the color version of the proof from Euclid. We then talked about, Lord help us, but okay, probably the color coding is going to tell us which part matches with which, but I have no desire to try to go through and chase that down. We then did the geometric proof where we had 4 right triangles and we formed a small square of side C and a larger square of side A plus B. And when you just go through the algebra, you get, after canceling, that a squared plus b squared equals c squared. And then Williams College, oh, I'm sorry, this was another way of arranging it. The next slide is the Williams College, we have to show Garfield. And this trapezoidal proof is completely different than the one we saw 2 slides ago. All right, so there's lots of different proofs. At the end of the day, do we know why any of these are true? So we did the dimensional analysis stuff, correct? Did we talk about dimensional analysis in Pythagoras? We did, right? Okay, so I'm going to skip all the dimensional analysis slides because we did those. And we talked about fielding equations. Did I give you this problem? Okay, so let's assume team A wins P% of their game and team B wins Q% of their games. Which formula do you think does a really good job of predicting the probability that team A beats team B? So if you look at these four formulas look very similar. What's the differences that you notice? Yeah, the sign. So there's two places where the signs can change. The numerator can be with a plus sign or a minus sign, and the denominator can be a plus in front of the 2PQ or a minus. So can anybody give me any thoughts as to how we might figure out which of these four is correct? Okay, why? Okay, so what must be true about all probabilities? They must be between 0 and 1. So when you're adding, there could be a danger of something getting too large. When I look at it, is there any one where I'm afraid it might be too large? Yeah, if I look at that one, I should be able to put in some values for P and Q so that the second one is clearly going to be a number greater than 1. I'm subtracting off the 2PQ. They both got a P, so I don't even care about what the P is. So I just need PQ to be greater than Q minus 2PQ. And you should be able to find a choice of Q that will work for that. So as an exercise, if you choose things appropriately, you can show that that second equation is wrong. The other ones get a little bit harder. So we're trying to figure out what's the probability team A beats team B. A wins P% of their games, B wins Q% of their games. Can you give me any cases where you would know the answer? So when might we know the answer? So you have team A plays team B. A wins P% of their time, B wins Q% of the time. Can you give me any values of P and Q where we should have an idea of what the answer is? Think of some extreme cases. What would be some extreme cases? 0, 1. So imagine A wins all of their games. Does it matter what Q is? It matters ever so slightly, which is the one value of Q we have to avoid. Yeah, if A wins all of their games, there's only one value of Q where we don't know what will happen. Yeah, if Q also wins all their games, if you have the two perfect teams placing each other, they're not both going to win. So when we look at this, if A wins all the games, if P equals 1, and Q is any number other than 1, what should the probability of A winning be? 1. So let's look at the first one. Go through and we can do the algebra. So we would have but then that's we have the people. So all right. This is not being recorded. Okay, so now the people at home can see this, and this is hopefully being recorded. Okay, I gotta talk back to Zoom. Okay. Okay, good. All right, so now we can start looking at various things. So if we look at the first one, Okay, well, I'm sorry. We already know the second one is out, right? So we know we can eliminate this one. Now let's look at the first one. When p equals 1, we get 1 plus q. And what do we divide by? 1 plus q plus 2q. So how confident are you about that? Is A winning 100% of the time? No. So at this point, I'm skeptical now about equation 1. What about equation 3? We would get 1 minus q divided by 1 plus q plus 2q. It's even worse, right? So if we look at then the third one, we would get 1 minus q over 1 plus q minus 2q is 1 minus q. So if I look at this, the only one that survives now is the last one. I'm going to kill all these. And so if I do that analysis, so that would kill this one, and that would kill this one. I claim there's some other values of p and q that would be useful to look at. So again, we've already got some evidence that it's the fourth one. But there's some other work we could do. Can you give me another value of p and q where we should know the answer? So if one of them is 0, you should never win. So if q is 0, it doesn't matter what p is. So we could go through and let's do the calculation when q equals 0. So when q equals 0, the first one would give us p over p, which works. The second one would give, we've already eliminated the second one, so I'll just keep the second one eliminated. The third one gives us p over p. And the fourth one gives us p over p. So it's a good thing to try. If we try q equals 0, nothing else. There's some other interesting values you could try. There's another very natural relation between p and q. If p and q have what relation should I know the answer? Okay, so if they're both 0.5, what should the answer be? So if p equals 1/2 and q equals 1/2, what should the answer be? 1/2. What if p and q are equal? What if A wins 60% of the time and B wins 60% of the time? What should the answer be? It should be 0.6. What if they both win 70%? Wait, it should be 0.6. So if A wins 60% of the time and B wins 60% of the time, how often should A beat B? Think about this. So if A is winning 60% of the time and B is winning 60% of the time, is there a difference between these teams? What should the answer be? 0.5. What if A wins 85% of the time and B wins 85% of the time? It should be 0.5. So if P equals Q, it should be 1/2. P equals Q should get 1/2. So for the first one, if P equals Q, we get P plus p squared, right? Divided by, we'll have 2p plus 2p squared. Well, when that simplifies, we get 1/2. For the third one, we would get p minus p squared divided by 2p plus p squared. So it'd be 2p plus p squared. What can you say? It's not 1/2. And then for the last one, better work, because that's the only one that's still around, we would get p minus p squared divided by, and we pull out the 2, and then we would have 2, because we have 2p minus 2p squared. Okay, that'd be p minus p squared. Good. That becomes 1/2. So we take p equals q, we should get 1/2, and that gave another strike to this one. There's one other special case that we can do, and I'm not going to go through and do the analysis. What if I give you q equals 1/2? What do you think the probability that A wins if q is 1/2? So A wins p% of the time. They play a team that wins half the time. So if A wins p% of the time against an average team, and they play a team that wins 50% of the time, what would you guess? I'm sorry, P, right? You win p% of the time against a generic team. We're playing a generic team. So I would guess that maybe it should be 1/2. I mean, it should be P, it should be whatever that P is. So let's just look at the last one. So for the last, if q equals 1/2, you get p minus 1/2 p. So the numerator is p over 2. What's the denominator? P plus 1/2 minus p, right? So the denominator is just 1/2. And with our knowledge of how to divide fractions, this is just p. This is not a proof, but this shows that it strongly supports the claim that the fourth one is correct. And again, when you get very large, complicated equations, if you can do smell tests, you can quickly look at it and ask, is this reasonable? What kind of test can I do? Is there a typo? Years ago, I was working on a research paper and I needed a result, and we looked it up in the literature, and it was something like the following. It's like the integral from -infinity to infinity of r. I mean, it was not exactly this, okay? But morally, it was something like this. What can you tell me about that integral? You actually know enough to be able to evaluate this after taking Calc 2, but I claim you should be able to just look at this integral and tell me what it equals. So let's plot x exponential negative x squared. I'm not going to go from -infinity to infinity. I'll go from -10 to 10. Close enough. And you see, you're looking at such a large scale, the function decays so rapidly. All right, that's too far. Let's go from -1 to 1. Or even better, I could use the manipulate. And I go from -c to c. C goes from 1 to 10. And so now I can increase c, and you can, what kind of function is this? So what kind of function is this? This function has a really nice symmetry. What symmetry does this function have?
Would just be 0.
Why would it be 0?
Because would be just the positive area equals the negative area.
Yeah, and what kind of function? There's a name for such functions. It's what? It's not periodic. Periodic means it repeats. This function, sines and cosines repeat. But sines and cosines are also examples of special types of functions. It's not saying. Approximately, what is its value at, say, maybe 0.8? Around 0.4. What's its value at negative 0.8? What's its value at approximately 2? Yeah, whatever those tick marks are. There's 1, 2, 3. There's 4 tick marks. It's probably about 0.4. Probably about 0.05. What would be its value at negative 2? So its value at x is the negative of its value at negative x. What do we call such functions? These are odd functions. So this is an odd function. F of x equals negative f of negative x. So integral over a region symmetric about 0 is just 0. An even function is f of x equals f of negative x. So if you think of your trig functions, can you give me an example of an even function? So what would be a trig function that's even? Cosine. What would be an example that's odd? Sine. So if I ask you to integrate an odd function over a region that's symmetric, what if I gave you, x cubed minus the square root, minus maybe let's do the square root of x squared plus 4x to the 4th plus 8. Oops, I would have put it in the wrong spot. So we'll do x cubed. I'm sorry, x cubed, and we'll have negative square root of x squared plus 4x to the 4th plus 8. Okay, this is not a pleasant function to try to integrate. We do not have ways to integrate this. I'm pretty sure I'll give it to Mathematica, and I'll ask Mathematica. Integrate, not interpreter, integrate this function with respect to x. Bracket. And I'm expecting, basically Mathematica says, what if I just display it nicely for you? Can I get some partial credit for just writing it like that? So I'll give Mathematica credit for trying to do something, but it's basically saying I am not going to integrate this. But if I try to integrate this, x goes from -10 to 10, it gets 0. It's able to notice that this is. Now, of course, you might be saying, well, maybe it's only approximately 0. And this would not be a proof, but I could say, oh, calculate it to 100 decimals. And it says, okay, I get it's 0 times 10 to the negative 101. All right, can you do it to 1,000 decimals? Sure. So I think Mathematica is actually smart enough to recognize that this is an odd function. And when it says it's 0, it says it is 0. It really understands that. Okay. So what I want you to get from this part of the talk is just the idea of how do we handle different equations. How do we get a sense of what's going on? Okay. So we can prove that the last one works. So over here, I just go through some different cases that we can look at, and we basically just discussed a lot of these. Okay. And so here is a way to prove this. So let's assume A has a good game with probability P and B has a good game with probability Q. So you win if you have a good game and the other team has a bad game. You lose if you have a bad game and they have a good game. What happens if you both have good games? Then you play again. And if you both have bad games, you play again. So this should remind you of the memoryless process we did when we did the basketball game, right? This is a really powerful concept. I'm trying to use the last part of this course to review, some of the key ideas we've seen. This idea of a memoryless process is extremely valuable. And so if they both have good games or they both have bad games, just play again. And you keep playing until one has a good outcome and one has a bad outcome. So what we can do is we can do like a little flow chart. So with probability 1 minus P, A has a bad game, and with probability P, A has a good game. We then do it again, and now we do what happens to B. And then B would have a bad game with probability 1 minus Q, and a good game with probability Q. Similarly, A would have a good game, if A has a good game with probability P, we have to show that underneath them as well. So we have 4 outcomes. Bad, 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 good, good, bad, good, good. What's the probability of the first one? That A has a bad game and B has a bad game. What would that probability equal? 1 minus P times 1 minus Q. Okay, we've got 4 people, 4 probabilities. Let's go around. What would be the bad, good, next one? But A has to have a bad game and B has to have a good game. 1 minus P times Q. Okay, we'll keep going. P times 1 minus Q. And then the A has a good game and B has a good game, the one on the far right. So PQ. So those are our 4 probabilities. Okay, and in 2 of them, we play again. And so if you want, you can just keep thinking that we just keep doing this, and eventually we have to end up in either a bad good or a good bad. This is technically what's known as a conditional probability. What is the probability that A wins conditional on either we have bad, good, or good, bad? So in a probability class, you'll talk about this all the time. One way you could do this is you could imagine you're doing this 1,000 times and seeing how often you end up in each bucket. And you would keep playing again. So as you do this more and more often, it becomes extremely unlikely that you have somebody that ends up in all bad, bad, and all good, good. So if we look at this, we can now calculate the probability A wins. So the fraction of times A has a good game and B has a bad game is P times 1 minus P divided by the sum of the 2 probabilities. Now, if you simplify the algebra, you get P minus PQ over P plus Q minus 2PQ. Phew, this is the 4th one. It's good that it came to this. But what's really interesting is that when you look at this, the way to look at this is not P plus Q minus 2PQ. So one of the goals of math is to try to figure out what is the right way to look at something. It's much better to look at it as P times 1 minus Q plus 1 minus P times Q. What I think would be a fascinating psychology experiment is to take a large number of people and give them these formulas. Half of the people get the denominator written in one way, half of them get the denominator written in the other, and ask them, can you come up with a justification for why this is true? And if you're given the denominator as P times 1 minus Q plus 1 minus P times Q, are you more likely to see a kind of probability tree like this? I think the answer is yes. I think it would be an interesting experiment, that how we are presented information can easily influence how you attack it. If you want as a professor, you can write exam questions in such a way to mislead people or to lead people. Does anybody know what a red herring is? So what is a red herring? Yeah, something to throw you off. I debated asking, does anybody know what a blue armadillo is? Which would be an interesting red herring, but that's fine. So depending on how the information is presented, it's really going to influence how you try to prove things. A lot of times when you're doing calculations, we want to simplify formulas because it makes it a little bit easier. I have no desire to do, the subtraction of 1 minus q, 1 minus p, that's 2 operations. Then I multiply that by p and q, that's 2 more, and then I sum, that's 5. Whereas here I have 1, 2, I have the p times q is 1, times negative 2 is 2, subtracted from q, so it's 4. So it's one less operation to do it the other way. But it really hides what's going on. Right. So special cases, can suggest answers. So we in class did the Bill James Pythagorean one-loss formula. This is a simpler model of trying to estimate the probability a team wins. Okay. And so, we've talked about this, so I'm not going to talk about this today. What I think I'm going to do, based on the time that we have, I'll just do some other gems, and I'll save extending Pythagoras for the last week, as just doing the multivariable there. I really want to emphasize trying to think about problems and trying to get estimates. I hope all of you will consider being math majors or stats majors, or if not, just taking a bunch of classes. I think there's a lot that you can gain from courses in this department. These are powerful worldviews. And if you're not a major, you can take some of these classes pass-fail. The goal is to get useful skills to know what's out there. But a lot of it is I want to really emphasize how do you learn how to think about things. The best is practice. The more things you do, the easier it becomes. And so I want to just talk a few things. So this is one of the more famous formulas in mathematics. 1 plus 2 plus ... plus n is n times n plus 1 over 2, which is approximately 1/2 n squared. It's 1/2 n squared plus n over 2. Okay, how many of you have seen this formula? Okay, so this is a formula that should be done at some point in your life. The story is that when Gauss, one of the top 5 mathematicians in history, was a 5th grader in school, the teacher was just having one of those days. And when you become a teacher, you will know what this is like, or if you have a job, you'll know what it's like. And the teacher wanted to shut up the little brats and told the young children under his care to add up the numbers from 1 to 100, because that would, take time, and he could then relax. And Gauss immediately goes 5,050. And the question was, how did Gauss add them up so quickly? As an aside, I still remember years later when I was in 2nd grade, we had 5 recesses one day. I didn't realize at the time, but I now realize what the teacher must have been going through that day if she kept sending us to the playground. So how did Gauss add this up so quickly? Well, Gauss's beautiful idea was that you could group. So if I take the numbers 1 through n, if I flip the order, if I go n plus n minus 1 all the way down to 1, it's still the same sum, right? And if I just put that underneath, then 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. All the way down to n plus 1 is n plus 1. So twice the sum is going to be n plus 1, plus n plus 1, plus n plus 1, plus n plus 1. So how many n plus 1s do I have? So how many terms do I have on the right? I have n, right? I have the numbers 1 through n. Each number gives me a pair. When you're doing slides, when you're doing presentations, use color well. I have been at talks in non-math fields where they just have so much pretty images and whatnot on the slides. They do a really good job of hiding the fact that there's actually no content in the talk. You want to have content, you want to have your images and your color and whatnot highlight what you're doing and not distract. And so here, well, let's put one of the set of numbers 1 through n in red, and in the reverse order, let's put it in blue, so that you can really look at this and see what's going on. If there's n of them, then that means that we have twice the sum is n times n plus 1. So the sum is just going to be n times n plus 1 over 2. And that's where the formula in the top line comes from. Okay. Any questions about this? All right, so what I want to do now is I want to try to make some guesses. And so we'll put this here, and I got to just switch so that it's now recording from there. Oops. Okay, good. Now it's showing up for the kids at home. So I want to try to come up with estimates. So if you want to be a smartass, this is your time. Can somebody give me a lower bound for the sum? I will take anything that's correct. You can be a real smartass and give me a real. We'll go to a more standard. Lower bound. Anybody want to give me a lower bound? I'm sorry? Why 3? Because we don't know what n is. But we don't know what n is. N could be 1. Okay, why 1? There's always at least one term. Okay. Can somebody give me an upper bound? No, 1 is not necessarily an upper bound. Well, I mean, if n equals 2, then the sum is 3. So you've got to give me an upper bound. But again, if n is 1,000, your bound doesn't work. How many terms do we have? N terms. What's the largest term? So can you give me an upper bound? We have n terms. The largest any of the terms is n. So what could the upper bound be? N terms, largest is n. So what? Well, but I'm sorry. Well, if the upper bound, let's say n is 100, then 1 plus 2 plus 3 plus all the way up to 100 is larger than 100. Your upper bound fails. But we have n terms, and each term is at most n. So if you have n terms and each one is at most n, how large could the sum be? That's n factorial. That will work, but you have to do a little bit of an argument to show that n factorial works. There's a much easier one that's a better bound. You have n terms, and each term is at most n. Let's do something explicit. Let's say you have 100 terms. So if you have 2n, just think about where we have n minus 2 plus n minus 1 plus n. So just the last 3 terms is giving you something of size 3n. Each term is at most n. So yeah, 1 plus 2 plus dot 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 plus n is less than or equal to n plus dot 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 plus n, right? Replace each term by n. And if we replace each term by n, what is the sum going to be? That will be n squared. So now we have an upper bound of n squared. We have a lower bound of 1. Well, we can actually do a better lower bound than 1. What's a better lower bound? So we use the smallest of all the terms. But we have the numbers 1 plus 2 plus dot 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 plus n. What's a better lower bound? N, right? Take the largest term in the sum, that's clearly still going to be a lower bound. So we know our sum is between n and n squared. The truth is it's about 1/2 n squared. So our lower bound is really bad. Our upper bound is really good. Our upper bound captures the correct n dependence. The problem with the lower bound is it's not the right order of magnitude. And we don't know which is the right, is it closer to n or n squared? So we have to either try to increase the lower bound or significantly decrease the upper bound. Given that I know the answer, let's try to work on the lower bound. So let's fix the lower bound. We have 1 plus ... plus n over 2 plus n over 2 plus 1 plus ... plus n. And I'll just assume n is a multiple of 2 just to make life easy. I want a lower bound. So if I throw away the numbers in the beginning, I'm only making things small. I'm only making it smaller, right? So do you agree that this will be true? Now, can you give me a number that's less than everything on the right? Something that's less than n over 2 plus 1, that's less than n over 2 plus 2, that's less than n over 2 plus 3, that's less than n. Yeah. So this would be less than or equal to, well, this would be, I guess, less than, and this would be strictly less than as well. Say n over 2 plus n over 2 plus ... plus n over 2. And how often do we have this? Have n over 2 times. So lower bound is n over 2 times n over 2 is n squared over 4. So the answer is between n squared over 4 and n squared. Oh, that's not bad. And so now, without being clever like Gauss, without doing proofs by induction, we now have the right order of magnitude. If you take the average, what's the average? How are you taking the average? Yeah, what's the average between n squared over 4 and n squared? I get, I think, 5/8 n squared if you do the arithmetic average. Right, 1/4 plus 1 is 5/4. Half of that would be 5/8. If you do the geometric average, you actually get 1/2 n squared geometric average. That's the square root of AB. So that's another way of doing averages, is you take the two numbers, multiply them, and take the square root. So the whole point of this is that without even solving the problem, we can do a pretty good job of getting a rough sense of what the answer is. One of these problems, that's all we need to do. So this is just learning it a little bit more nicely, that we have n halves of the terms are at least n halves. So it's somewhere between n squared over 4 and n squared. If you want to do even more work, you can do the shampoo method. We've talked about shampoo, lather, rinse, repeat. So what we could do is we could divide it up instead of into the first half and the second half, first quarter, second quarter, third quarter, fourth quarter, and do our analysis for each of those. And if you do that, you would get 3/16 n squared as the lower bound. I'm sorry, you get 6/16 as the lower bound. That's much better than 1/4. It's getting closer to the 1/2. And so then instead of doing it 4 times, what could you do? 8. And the question is, and I'll make this extra credit, can you make this argument rigorous and do it well enough to prove that the lower bound converges to 1/2? And similarly, that the upper bound should then, by a similar argument, should also converge to 1/2. And so can you use this to prove that it will go to n squared over 2? If you've seen the factorial function, which was a really nice thing to try, n factorial is n times n minus 1 times n minus 2 all the way down to 1. And the question is, how rapidly does the factorial function grow? Well, we did this in class when we did the integral test. And you should have a Pavlovian response. Whenever you see a product, what do you think of? Logs, right? So whenever we see a product, we think of logs. If we take the log of n factorial, we get the log of 1 plus the log of 2 plus the log of 3, all the way up to the log of n. That's approximately the integral of log of t dt from 1 to n. By the integral test, this is then t log t minus t at 1 and n. And when you go through, you get it's of size roughly n to the n e to the minus n. N factorial is about n to the n e to the minus n. If you do a little bit more work, you get it's n to the n e to the minus n square root of 2 pi n. How many of you have done statistics? Do you know where you see a 2 pi in statistics? The Gaussian, the normal, the bell curve. Its normalization factor is a 1 over square root of 2 pi sigma squared. It's coming from Stirling's formula. It's related to that. And so you could try to apply arguments like this to estimate n factorial. And you can again get something very close to n to the n e to the minus n. All right. I will just end. We've got, I think, 2 minutes left with one of my favorite gems. So how many of you have seen a proof that the square root of 2 is irrational? So you cannot write the square root of 2 as the ratio of 2 integers. I'm sorry? No. No, I is the square root of -1. So if you try to write the square root of 2 as a ratio of 2 integers a over b, without loss of generality, you can assume a and b have no common factors. And then you would get root 2 equals a over b. So root 2b is a, so 2b squared equals a squared. You then show that 2 divides a squared because a squared is even. If a was odd, odd times odd is odd. So 2 divides a. So then get 2b squared equals 4a prime squared. Then that means 2 divides b. And wait, but we assumed a and b were relatively prime, so this is a contradiction. So this is a geometric proof, and I'm going to just leave it up here. I'm not going to go through this in detail, but you can say, well, if we assume that the square root of 2 is rational, we could write some squares like this, and you would have this region in the middle that's double counted. And you would have the 2 white regions which aren't counted at all. So you would then get the area of this square has to equal the sum of those 2. And you would get a smaller way of writing the square root of 2. And so it's interesting to see just how far can you push this. If you haven't seen the square root of 2 as irrational, this is something that's often done in high school. If it's not done, I don't want to talk too much about this. The whole point of this was to just highlight the power of different ways of looking at things. But if you haven't seen the square root of 2, all this is going to do is make you think, well, I haven't learned that. So I'm not going to say anything further about that. So this is a good place to stop.